at 15-minute increments. All right. If I toss the ball straight up in the air, at the top, assume it's going straight up in the air. At the top, what sort of velocity at the top? 0. Okay? If we throw something up, we throw a ball straight up, at the top, Vmax, Ymax I should say, y is equal to 0. Okay. This is a fact. This does not change regardless of anything else. So, if I am throwing the ball across the room, and I look at the ball at the top of its motion, okay, we still have Ymax, Vy equals 0 at Ymax. This is whether it's going straight up or whether it's going in a curve like this. Okay? Regardless, and this is a fact. You didn't even have to calculate this. All you had to do was say at the top Vy equals 0. All you had to do. Okay? That is what I'm supposed to be teaching you, and I'm sorry that I didn't get this kind of thing across. So this particular problem uses a couple of physical situations that lets us take a shortcut. Okay? The other shortcut is, what is the velocity right here when it comes back down? Okay? The velocity at this point is exactly the same as the velocity at this point. Okay? Is equal in magnitude. Okay? Is equal in magnitude. Okay? If I'm throwing my ball directly up, okay, so we have V equals 0 up here, Vy equals 0 up here, y equals 0. What is Vy when it comes back down? Well, Vy is simply equal to the negative of Vy initial. Okay? It comes up, it goes up, it comes down. Okay? So at the second one, so V at A is, so we know Vy is equal to 0. Okay, and Vx is simply whatever our original Vx was. In this case, it was, what was it, 10 meters per second? 15 meters per second. So if our original, so if this is 15, this was 53 degrees. This is a 3, 4, 5 triangle. Okay. Again, I threw this one in here because we talked earlier about special triangles. There's 3 special triangles we should recognize. We should recognize a 3, 4, 5 triangle. You should recognize a 45-degree triangle. And you should recognize a 30, 60, 90 triangle. Okay, so these are very common. We will see these all over the place, okay? So, or you can simply say that Vx is equal to V cosine of 53 degrees. Okay. This is 5 times 3. This would be 3 times 3 or 9. This would be 4 times 3 or 12. Okay, is equal to 9 meters per second. Okay. So at A, at the top here, our vertical velocity is 0, and our horizontal velocity isn't changing because we have no acceleration. Okay, so Vx is equal to constant. So 1, we know Vy equals 0 at the top. 2, we know Vx is constant. 3, we know that Vy at y equals y naught, okay, is going to be negative Vy and naught, okay? So our velocity, if we throw our ball up in the air, comes back down the same point, it's going the same velocity we started with, okay? But in the opposite direction, okay? So we don't even need to know the details of the motion. We just know that at the top it's 0, and at the bottom it's the same we started with, okay? The last part is, of course, more difficult because the last part we actually have to use our kinematic equation. That is for part 1, 2, and 3, A, B, and C. So for C, okay, we had, so here is point A, point B is at y0. Okay. And here at the ground, y equals 0. And so only for the last part do we actually need to pull out the kinematic equation, which is delta y, I guess I should say y. That's not a y. Is that velocity in the y direction, okay, is velocity at B, velocity at B minus, now, there are 3 kinematic equations. There is a kinematic equation for position as a function of time. Plus 1/2 a t squared. There's the velocity as a function of time. Naught plus a t. And there's a third kinematic equation in velocity that we don't use time at all, okay? And that is v final squared minus v initial squared is equal to 2g x final minus x initial. Okay? We could write this as 2g delta x. But this is not delta v squared. Okay, this is not delta v squared. Delta v squared is v final minus v initial squared. Okay, so our third kinematic equation, that is v final squared minus v initial squared is equal to 2g delta x. Okay. This one actually comes from these two. We take this one, solve for t. T is equal to v final minus v naught all over a. Okay. We plug this into here. So we've got x final minus x initial, all right, so is equal to v naught, and t is v final minus v initial over a, okay, plus 1/2 a t squared. Well, v final minus v initial over a, square that. And then we do some algebra, And algebra will get us here, okay? Part of the thing is we have a V final rather, minus V naught squared. So it's V final squared plus V naught squared minus 2 V naught VF, okay? You'll get a term for this on both sides, and this goes away, okay? If you plug in this one here, this gives you a V naught VF term and a V naught squared term. Okay? So what you're left with after all of the algebra is this. Okay? This is really the equation that would be handy for this particular situation, because we know what the velocity is here. We know this. Okay? We know what our delta y is. We're given delta y. All right? And we know g. Okay? So all we need to do now is find out what is our v final. Okay? I realize we have not used this equation a whole lot in this class. And I don't have any particular reason for not using it other than we don't seem to have problems in the problem sets. Question?
So really quick, have you like written this equation up on the board before? Because I write down all the equations you write down, and I didn't have that one, so either I missed it.
This no, but we have actually at least seen this a couple of times. Pretty darn sure. We may not have used it in a whole, but I think we've maybe used it in one problem.
I'm not sure you've ever done it, you've never worked it through, but you've definitely written it.
Okay. My bad. Okay, that's something that I am going to work on today then. This is why we do quizzes as a matter of, finding out where y'all are, as opposed to, quizzes and tests are not here to make you unhappy. That's just a benefit, okay? The real reason is to get some feedback so that I know where y'all are, so I know what we need to go back and go over, or what I just didn't really give enough time to and needs some serious attention. So, right, so our third kinematic equation is what we can do, is what we use if there's no time. No time given. All right. Some more. What's my time look like here? A minute and 20. Okay.